Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi, everybody. Thank you for coming. This is Chris Olson. He's coming here from Yahoo Research. And today he's going to give us a talk about some of the work he's done in web scale processing. And I'll just, I think, let him get going on that. Thank you very much. Thanks, Chris.
Okay, thanks, Emily. Yeah, so I'm here to talk about pig, and you'll know what that is soon enough. So I have a sort of a complicated diagram that I draw to motivate the work. So this is going to require your attention inside the rectangle. So look, there's been a lot of excitement lately about the need to just, in general, deal with very large data sets and all the ramifications that has. And certainly Yahoo and Google and Microsoft, a lot of the engine of innovation, so to speak, a lot of it comes from taking very large data sets, being able to analyze them and derive new knowledge and exploit that and make money. And right, so this work is sort of part of the overall sort of theme over the last few years of people trying to figure out ways to derive value out of very large data sets using large-scale systems. Okay, so in a little bit more detail than my last picture, right? So we have these projects that are where we're trying to, derive value from large data sets. You have two kinds of things roughly. I mean, you have cases where you have unstructured data and you're trying to derive structure, right? So we don't really do this so much at Yahoo, but you have images and you want to derive, people from those, right? Or maybe you have data that's already fairly well structured, but you want to understand it better, right? Maybe this is just a very complicated system that the data is from. So you have these complicated social systems and economic systems and computer systems. You want to try to understand them better, right? I assume I'm preaching to the choir here, right? So we like to say data analysis is the inner loop, and at least for some part of Microsoft, that's probably the same thing. And as we all know, so now you have big data. You want to do big processing. Parallelism is the name of the game. Okay, so some concrete examples that I'm going to use sort of as running examples throughout the talk. The first one is sort of the hello world kind of equivalent. It's just very, very simple. Brain dead parallelism is that you have some function, you want to run it n times, n is big. Each invocation is independent, right? Very simple. A slightly less simple one is you have some web data, like you've crawled the web and you've recorded people's clicks. So you have these two big data sets. And there are lots of interesting analyses you can do over these data sets, but I'm just going to pick one as an example. You're interested in finding sessions of consecutive clicks by a given user, and you want to find sessions where the last page that was clicked on was better than the others, according to some metric of goodness. Okay. So just these are the kinds of things we want to be able to do. We're not the first people by any means to work on these kind of problems. So there's obviously work from the hardware to the software side, parallel architectures. People have looked at data parallel software for many decades, parallel databases, MapReduce, Dryad, of course, done at Microsoft. And of course, even on the language side, SQL is data parallel language from a long time ago. There's stuff from the programming languages community on data parallelism. Okay, so what we're doing is building on a lot of the existing technologies and trying to do something that really fulfills a sort of a sweet spot that we see in the way people are processing big data sets at Yahoo, and I suspect that generalizes not only to the other three gym companies, but to the sciences and government and all of these areas where people are dealing with very large data sets. So, as I go, I'll make references to this large body of prior work. So the project is called PIG. Don't ask me why. It just is. PIG's not. Usually people think PIG is an acronym. It's not. It's just a farm animal. But so there are two aspects to the project. Okay. We have a data parallel language. The language is called Pig Latin. And roughly speaking, it's the combination of these three aspects that make it powerful and make it useful. And as you'll see in the talk, people actually do use this a lot at Yahoo. So the first is that we have relational style primitives for manipulating data. So if you don't know what that means, it's like filter and join and the sort of set-oriented primitives. Okay. The style of programming is more of an imperative sort of step-by-step style, okay, which is different from what you see with SQL. And the third thing is that we make it very easy to plug in custom processing, right? And you can interoperate with legacy code, all those things, which in practice makes a big difference. Okay. So it's the combination of those three aspects that make it work well in practice. Okay. And I'll talk about the language in sort of the first half of the talk. And then I will talk about our implementation, which is called Pig. And there's a lot of boilerplate stuff here, which I won't bore you with, but I will talk about some stuff that's a little bit more on the research side that has to do with optimizing ensembles of programs. Okay, so I'll get to that more at the end. So starting with the language. So remember our simple detect faces and images example. Okay. So here's a very simple Pig program that is going to take a set of images, potentially a very large set of images, and do face detection. Okay, and I'm going to walk you through it. My goal is not for you to understand the syntax, because you can look it up in our syntax manual, but just to give you a flavor for how the language works. So don't focus too much on small details of the syntax. But the basic idea is that there are 3 lines. Okay, each line represents a distinct command, right? And that's a distinct operation on data. The first one is simply specifying where the input to the computation is going to come from, right? So you're saying load. You're giving a pointer to a file or maybe a directory containing a set of files in some underlying file system. That could either be a local file system or it could be a distributed file system like the Google file system or the Hadoop file system. Okay. Here you're specifying some code that is able to parse this file or set of files into structured records. Okay. And here you're actually specifying what that structure is. So you're saying, well, it's a bunch of pairs of ID and then the bytes of the image. Okay. And then the assignment on the left, you're saying, well, I'm going to create a variable called I, which stands for the set of all such records that were extracted from this file. Okay. And so on the left side, I'm going to have these variables that stand for sets of records. Okay. It's important to realize that these variables are not instantiated anywhere. They're just conceptual. Okay. So fine. So I is sort of the parsed data set. And then the next command is saying, well, look, I want to apply some operation on each instance, or each member of that set. And in particular, I want to run my detect faces code on it, on the image. And then I also want to pass along the ID so I know which image that came from. Okay. So F is just going to be the set of ID and face detection output pairs. Okay. And then the last line is I'm saying, well, I want to take this set F and I want to actually materialize it in my file system. Okay. And if I do it like this, it'll just use some default formatting. If I want to have some custom way of laying it out in the file, I can, right? Similarly with the input here, I can specify some code that will lay it out however I want, right? And these input and output code things are very important in practice because they help you interoperate with other tools. Okay. So this is supposed to be simple. Hopefully everyone understands this one, so we can get to the next one. Any questions about this one? Okay. Good. Great, so that's simple. So here's a slightly more complicated one. Remember, we had this notion of sessions, and we wanted to find sessions that end with the best page. So you've got these 2 very large data sets. One is a data set of visits of users to web pages. So you've got these triples that say, Amy went to CNN at 8 a.m. Right? This is all fictitious, of course. And then you've got this other data set, which is all the web pages in the universe. Right? So you've crawled like 10 to the 10th web pages. And for each page, you can extract all kinds of information from that page, right? You'd have many columns. Just for now, let's assume that you've extracted just the page rank of each page. And you've computed the page rank, right? And so you have these 2 data sets, and obviously if you combine them, you can answer that question. Let's define the best page as being the one with the highest page rank. And let's define a session as being a sequence of clicks by the same user that are not divided by more than an hour, right? Okay. So look, if you read some old books or papers on parallel algorithms, from like the 80s, you can figure out how to do this in parallel, right? Let's assume that these visits and pages data sets are large, so we're going to initially store them instead of on one disk, on an array of disks. So we'll have like 1,000 disks, each storing 0.1% of the visits, 1,000 disks each storing 0.1% of pages. Right? Fundamentally, to answer this question, we need to be able to associate page ranks with the clicks. right? And then we can actually do the processing. So the first step, the data is sort of flowing up here in this diagram. The first step is we need to do that matching of pages with visits according to the URLs, right? And in databases, it's called a join. One way to do it, there are many ways to do it, but one way to do it is you allocate like 1,000 compute nodes. That's what these boxes represent. And you take one record out of here and you send it to one of these places, right, by looking at the URL, maybe applying a hash function or some other function, right? You do the same thing over here such that, records with the same URL are going to rendezvous at the same node over here, right? Probably most of you have seen things like this before. Okay. And so what happens is all the CNN records go over here, all the BBC records go over here. You do the matching locally after that point, right? So now you know the page ranks of every click. The problem is now you've mixed up all the data based on URL. What you really wanted to know was for each user, what were these sessions, right? So then that's fine. So we're computer scientists, so we'll just use the same trick again. So we'll allocate a bunch of nodes up here. We'll redistribute the data such that all of Amy's records are here, all of Fred's records are here. Once we've done that, the rest is all local, right? We can apply some sessionization heuristic to Amy's clicks, and then we can look at, there's a very simple script that any of us can write. It's like 5 lines that tells you, is the last click in a session the one with the highest page rank or not? Okay? So fine. So parallel algorithm, it'll be really fast even if the data is big. Okay? Obviously, what we're going after here is that we want things to execute in this manner, but we don't want to write this code. We don't want to write the distributed code because it's hard to write and it's even harder to debug, right? So this is a Pig Latin program that causes the execution that I showed you on the previous slide. Okay. And again, my goal is not to go over the nitty-gritty details of the syntax, but just to give you a flavor of how this works. Okay. So there are these 2 load commands because we had 2 data sets. So let's say the data sets were initially in these 2 directories. The web is kind of yucky, so it turns out that URLs, you can have many different strings that actually semantically represent the same page. So there's this process of canonicalizing or normalizing URL strings. So let's say you have a function that does that. So what we're doing here was once we load up the visits, let's say that we know that in that data set the URLs have not been canonicalized. So the first thing we do is say, okay, for each of these visits, we want to canonicalize the URL, right? So now we have the cleaned up visits. Let's say in pages it's already stored in canonicalized form, right? So the next thing we need to do is perform this join. We have a command called join that takes visits and pages, and here we can say we want to join them based on URLs. Okay, so VP is the set of visits joined with pages. Okay, and then what we want to do is we want to group those records according to user. So now we're going to take this very large flat set of visits matched with pages and divide it into subsets, one for each user. Okay, so user visits is like the set of subsets. Okay, and then for each of those, we want to run some code that finds sessions using our heuristic of looking for gaps in time, right? And so now we have sessions. And then lastly, we want to filter sessions, which means we're going to take a set and we're going to find a subset. And here we have some predicate, some function that returns true or false, which just looks at, okay, is the last click the one with the highest page rank or not? Okay. So what's going on? So you're invoking transformations on sets of records to get new sets of records. These transformations have names like join and group and for each. I've pretty much shown you the whole language. So there's only a handful of transformations, and this is pretty much the whole thing. Okay. The power is that you have a small number of transformations, but they're governed by these functions that users provide. So you're doing filtering. You can filter according to either a built-in kind of predicate or according to a custom user function. Right? And similarly with joins and with all the other commands. Okay. Any questions about this program? In the back?
Why did you not use the...
You're not in the back, but that's okay.
So why did you not use the terminology like map or reduce and decide to use join and...
Well, but you could ask the MapReduce guys why they didn't use relational terminology. I mean, at some level, they're all the same. Yeah. I have a slide on that, Arvind. Okay, yeah, so usually Usually somebody asks one of each of those questions. Okay, so I will get to the relationship to MapReduce in a second, and also the relationship to SQL. So, but for those of you who, well, so I mean, just to summarize what I just said, look, we have transformations on sets of records. The idea is that we pick the top 10 things that people do with data, right? You join and filter and project and so on, right? And the idea is that okay, these are easy for users to use. They're extensible. You can filter according to some user-defined predicate, etc. We've also, of course, chosen primitives that we know how to parallelize, because the whole point here is that you should not be able to write programs that are slow if the data is big, right? And just roughly, I've shown you most of the operators. You have ones that take one data set and produce a new one, like filtering. For each is the most common one that just says apply some arbitrary processing to each record to transform it. Grouping is going to form subsets, right? We also have operations that combine multiple data sets. So like join, I showed you. Co-grouping is another one that's related to join that I'm not going to go into in this talk. Union is like the set union. So, fine. Okay, so getting to Arvind's question. Yeah, so there's a bunch of other languages that are related. So let me talk about SQL first. So certainly the types of operations you can express are well, to a first approximation, the same as SQL. There are some differences that I'm not going to go into now, but our paper talks about that have to do with nested data. But at a high level, yeah, it's the relational operators, right? Join and filter and whatnot. So it's not so much the expressive power. It's more that with SQL, there's this strong sense of it's being declarative, and the user has no business knowing or specifying how things are executed in the system, right? That's the job of the query optimizer, okay? And the idea is that the query optimizer is going to produce a very well-chosen plan for how to execute it, okay? And so there's this notion of separating those two layers, which sometimes works very well and other times does not work as well. So with Pig Latin, rather than in SQL, you specify this bundle of constraints that are saying the answer will have these properties, right? But I'm not going to tell you how to compute it. With Pig Latin, you're giving a sequence of steps where each step is transforming the data. Okay, now each step itself may be considered declarative, but you're giving the order of the steps. Okay, so it turns out that first of all, just in terms of programming style, it feels a little bit closer to imperative programming. So like if you're writing a Java program, right, you have a sequence of steps where each step gives you a new variable, right? And some people coming from sort of a non-SQL background find it easier to understand this way of programming than the SQL way of programming, okay?
So maybe I can ask a question similar to Arvind's, which is,
yeah.
In our world, between dry and link and between SQL, I'm trying to see where Pig Latin really fits in. Is something else in between, or so I could say Radling gives you the ability to integrate well with programming languages.
Yes.
Yet you can invoke high-level operations. And
yes. Yes, agreed. Yeah. So I think dryad link, correct me if I'm wrong, to a first approximation, it's SQL with a better integration with higher level languages and the ability to compile down into dryad. Okay. So so the idea with Pig Latin is you're specifying a Dataflow graph. Then you can think of it as roughly analogous to relational algebra, as opposed to a more calculus-like expression with SQL. So that's the way I explain.
Relational algebra
yes.
Lightweight. The SQL syntax is kind of a hodgepodge of algebraic and declarative stuff. So
yes.
Think about it as a clean version of algebraic. If you have to expose what everybody does after parsing in the optimizer,
yes.
It's roughly that representation you're using.
Yes. Yes. When I'm talking to a pure database audience, that's usually what I say. But yes.
Maybe we've got a similar question from a programming language perspective.
Okay.
The examples you've shown, you describe them as imperative, but they look like pure functional programs to me in the sense that they always create new variables, they never overwrite them.
Yes. So again, I guess it's functional. So from a database perspective, database people see the world as having exactly two models. There's declarative and imperative. But yes, you're right. It's functional in the sense that each one produces a new variable. You can overwrite variables, and there's no side effects. Yes. Okay. So there's really two distinctions from SQL. One, the difference is it's really like relational algebra, and that gives you two things. One is that programmers who are used to writing programs as sequences of steps prefer that model. And I'm not just making this up. Like, so people actually tell me, like, look, I prefer, just as strictly a stylistic issue, nothing to do with performance, I prefer writing things in this way. But the other issue is that you're one level closer to the execution compared with SQL. So you have more direct control over what's happening. And when you hear people sort of on blogs and so on talking about why they like MapReduce, like when certain database people write comments, provocative comments about the two, I'm sure many of you have read these blogs, right? What people will say is, well, look, I want to be assembling pipes. I don't want to be writing logic constraints. And so what we want to do is retain the aspect from MapReduce where you have these pipes, but bring it up to a higher level where you have these sort of general data flows instead of the sort of rigid two-step pipe that you plunk down, right? Okay. Any other questions about this Pig Latin and SQL distinction? Yeah. So if you're a database person, you can think of it as relational algebra, but there's some secondary stuff that has to do with nested data. Okay. So if you're not a database person, you might care about this. So how does this relate to MapReduce? So MapReduce is giving you a data flow that has three sequence of these steps, right? So you're saying, I want to process records individually, I want to form groups of records, and I want to process groups, right? This is called the map step. This is called the reduce step. This middle part is implicit. Okay. So first of all, like, Pig Latin subsumes this in the sense that if you give me a program that's structured as a map function paired with a reduce function, I can write a simple pig program that will give you the same output you get with MapReduce. So, so you're saying, I have some input, so for each input I want to apply my map function, and then I want to form groups according to, so in MapReduce, all of your records have two fields, a key and the value. So in Pig Latin, you can refer to fields either by name or by position. So $0 is a way of referring to the first field. Okay. So I want to group by the first field that comes from the map function. And then for each of the groups, I want to apply my reduce function. Okay. So certainly this subsumes the MapReduce model. And what you're getting here is that in Pig, each of the steps is explicit, and they're independent. You can compose them however you want, as opposed to being stuck with this sequence of three things in that particular order. Okay. And then on top of that, you have, as I said, you have primitives for the things that people do all the time with data, like filtering, projecting, combining multiple data sets. Okay. So I would argue later I'll show you some of the numbers that we're seeing in terms of usage at Yahoo, but I think this is a much more natural way to write programs than using directly MapReduce. And the other thing is that because it's a higher level language, there are more opportunities for the system to be able to do some optimizations. Okay. So in terms of our implementation, what we do, so we have our Pig system, which you can compile Pig into local programs. Right? And people typically do that for debugging. But the real power, of course, is that you want to run it on a cluster. So we layer Pig on top of a Hadoop MapReduce, which is then running on potentially clusters of thousands of machines. And users, of course, they're not blocked from using MapReduce. They can use MapReduce directly, or they can use Pig. I put the SQL layer on top in parentheses. We don't have anything like that implemented, but it's not hard to imagine that a layer like that will someday come into existence. Right? So I think in a year you'll see that either from Yahoo or from somebody else. Okay. And I think there are good reasons to be at each of these levels. Okay. So if you're a database person, because database people famously think everything is a database, and I'm a database person too. But if you look at this, you'll say, oh well, you're building a database, right? You'll say, well, right, because if you take Microsoft SQL Server or Postgres or Oracle or any of these systems and open them up. Right, if you look inside, well, yes, the highest level is SQL, but inside that, you'll have something that compiles SQL into relational algebra trees, which to a first approximation is what Pig is. And then underneath that, you'll have these sort of physical implementations of the relational operators, which to a first approximation, that's what MapReduce is doing. Okay, it's doing group by, and it's also giving you a substrate that lets you do joins and things like that. Okay, so the question that I get from database people and from myself is, okay, so are we building another database system, or is this different? How does this relate? Okay, so is this a database system? So I don't think the answer is yes or no, but what I'm trying to do here is take 4 interesting dimensions. I'm not trying to be exhaustive, but I think these are 4 important dimensions. Okay, and so in terms of the workload, right, database systems typically try to be very general. So, right, they're saying, well, look, I'm going to be able to deal with, sort of large bulk reads and writes, and also random reads and writes, and all kinds of different access patterns, right? And as part of that, I'm going to have all these mechanisms, right? So to deal with random reads, I'm going to have indexes to make those efficient, and because I have writes, I have to worry about multiple users, or sort of concurrent users, stepping on each other's toes. So I'll have all these mechanisms to give you nice properties in terms of concurrency, right? Transaction mechanisms. So if you look at Pig and MapReduce and Hadoop and those kinds of systems, right, what they're doing is they're saying, look, I'm going to handle a much more restricted class of workloads. I'm going to disallow writes, or I'm going to have a very, very constrained form of writes. And I'm going to focus on only sort of large sequential reads, right? So typically you're making one or more complete passes over some large data set, right? And, so really what's going on here is you're taking a slice of the workload and you're trying to make it, especially scalable and especially fault tolerant and all of those things, right? So there's no magic. You see this all the time in computer science, right? If you work on a more specific problem, you can maybe do better in some dimension like scalability, for example, right? Now, in terms of data representation, right, in a database system, there's this notion of loading the data into the database system. So you give the database system the data. At that point, it sort of lives in the database system, and it's controlled inside there, right? And there are good reasons for that, because it makes transactions easier. It helps the database system do query optimization. I mean, there are all kinds of reasons why that's done, right? But it also means that there's a higher barrier to actually do the processing, right? And there are various implications of that, right? It also means that it's more difficult to deal with loosely structured data. Okay, so certainly what's happening with Pig and MapReduce and those kinds of systems is, look, the data resides in files, and yes, maybe they're distributed files, but the abstraction is a sequence of bytes. And yes, the user will, at various times define various structures on top of that, but they're not fixed to any one structure. So typically the structures are defined on a need-to-know basis. So you'll say, yes, do this join, and for the purpose of this join, here's the structure of the data, right? Just go. Okay. So it's a little bit more free-form in that sense. And I already mentioned this programming style. So DBMS typically deals with SQL kinds of things where you have a system of constraints that define the answer. Right? Where here you have a sequence of steps. And I would argue that programmers are more likely to prefer this model. Okay. And lastly, right, in terms of customized processing, yes, you can express user-defined functions in SQL. Sometimes it's very awkward. You have things where like the signature of the function determines which of the SQL clauses the function goes in. And sometimes people have a hard time reasoning about that. In Pig, we sort of started with user-defined functions, and we designed the language around that. So they're very much first-class citizens. We also have the ability to interoperate with legacy code. So you have some executable sitting there that does face detection. You don't even have the source code anymore, but it works. You just want to pump data through it, right? And you want to interleave that with some more structured operations like maybe joining and filtering, right? And with Pig, that's very easy to express. Okay. So any questions about this characterization?
Do you have any sort of restrictions on the custom functions?
Any restrictions on the custom functions? Not formally, but if they have side effects, you might get weird things. Yeah, in the back?
So can you explain why indexes are not applicable to this model?
They are applicable.
There's sort of an investment you can make when you read the same
Sure.
message more than one time, right?
Yes, and certainly for joins, there are cases where indexes can be very valuable. Yeah, I'm not ruling out indexing. In fact, people are working on indexes in this context, like HBase and things like that. But what I'm saying is, if you just take the core system, right, it's what is it good at? It's good at doing very large sequential scans, right? And it's right. There's a difference of approach where here is more of a bottom-up approach. Like let's stick to things that we know we can do really well. And let's take that as far as we can go. Whereas here it's more top-down. It's like, let's define this very broad set of things that you'd like to be able to do, and this very nice set of properties like transactions and whatnot, and let's see how efficient we can make it. Right? So I think it's just sort of a top-down versus bottom-up. That doesn't mean you can't add indexes to this world. Right? And people will, right? And people are doing that. All right. So sometimes people ask me, how do you actually run pig? So I've shown you like how to run it in PowerPoint, but so like if you're actually sitting at a computer and you want to use pig, what do you do? So briefly, so typically just if you're getting started, you want to play with it, you can get the interactive shell, you get a little caret, you start typing, load, filter, whatever, right? If you're doing anything serious, you probably have your pig script in a file, and you give it to pig, and pig runs it for you, right? You can also embed pig in a host language, such as Java. Actually, right now it has to be Java, but there's no fundamental reason for that. Okay, and you would do this if you want things like Turing completeness, right? You want loops on the outside of your pig program. So for example, you can implement PageRank. PageRank is about 6 lines of pig, but that's for one iteration. So you need some kind of a control loop on top of that to do the iterations, right? There's no fundamental reason you can't have control loops in pig. It's just we didn't implement it. Okay, it's very rare that people actually need that. And we're also working on a graphical editor to be able to sort of graphically specify with the boxes and arrows diagram, a pig Dataflow. Okay, this is a real thing. We've implemented it. It's available in open source. We have it running on Hadoop, or you can run it on your local machine. People use that for testing, as I said. Okay, it's production quality. People are using it for real stuff, but it's also we know there are some problems that we're working on fixing. So just a little disclaimer. This is being used quite extensively at Yahoo. So at this point, we have hundreds of users collectively submitting thousands of jobs per day. Okay. And recently we did a measurement. 30% of the Hadoop jobs that are being run at Yahoo are coming from pig. Okay. And this is after less than a year of pig being in production. And the number is increasing every month. So that's not the, it hasn't reached its maximum. So what this means is that, people are jumping onto this relatively young system, because they're looking for higher level abstractions. And people are saying that it's making them more productive versus using raw MapReduce.
So the remaining 70% are they using MapReduce?
Yes, the remaining 70% are using MapReduce directly.
So pig basically takes pig-Latin and reduces it to MapReduce.
Yes. Yes. So remember this picture. So this arrow is a pig Latin program, and pig will compile it into one or more MapReduce programs. Okay. Sergey.
To get a sense of complexity reduction, do you have an example that shows a pig program and the MapReduce program side by side so you can kind of see it?
I don't have an example off the top of my head, but writing a join algorithm is at least a few hundred lines of code, and it's one line in pig. So, and a lot of programs involve joins, at least at Yahoo. So a couple orders of magnitude. But but people cut and paste those things, so they're not always writing them from scratch. And it depends how you want to measure it. Yeah. Okay. Emery?
In terms of that 70% versus 30% number, I'm curious in terms of this getting my mind around adoption.
Yeah.
How much of that 70% of those jobs are old jobs that are just being rerun every day?
I know it's more than 0, but I don't know the number. Yeah. So the question was, some of these jobs are maybe ad hoc processing, but a lot of them are probably sort of just nightly jobs that are just run systematically, maybe run on new data every night. And so the question was, some of the 70% Hadoop jobs are maybe just inertia from stuff that's been running every night. Probably a lot of it, but I don't actually know. Yeah. Okay. So at this point in the talk, I'm going to start getting gradually more and more into researchy things. So far I've been describing something that's mostly just a practical thing that, it's sort of, it's trying to get the best of both worlds between a MapReduce kind of scenario and a SQL kind of scenario that works for a large class of developers. They like it. Okay. I don't think there's anything especially deep about it. Yes?
You said, just before you started that, I just wondered, you said before that method should not make updates, but you don't check that. What sort of error checking do you do at all, or is that going to be part of the talk?
What sort of error checking do we do? Right now, we actually don't do a lot of error checking, and that's one of the things that we're trying to improve. So I guarantee that Dryad is way more far ahead in terms of error checking and things like that. Yeah. So there's a team of like 6 programmers working on error handling and error checking and a lot of issues like that. So it will get better over time. Yep. Yeah, so I should mention, so Pig started purely as a research project in Yahoo Research, and at this point it's purely a development project. So Yahoo Research is involved, but mostly we sort of handed it off, and we're working on other things. So the developers are much more likely to come up with good ways of doing all of those things, especially since none of the researchers are programming language people. Okay. So what I'm going to do now is start talking about things that are more researchy that we're still working on, and this less tested stuff. So one of the things that we'd like to have is a development environment for this kind of thing, right? So you can imagine, I mean, most of this is like boilerplate stuff, right? So you want some environment that tells you what data is available. It gives you libraries of processing elements, things like that, right? And as part of this sort of graphical tool, you can imagine ways of building up Pig programs other than textual programming. You can have sort of boxes and arrows, ways of specifying it. And along with that, we can display example data for you to help you build up your program. Okay. So this stuff is kind of boring, so I'm going to talk about this stuff and give you some examples. Okay. So, and this gives me a sort of a sneaky way to give you another example of a Pig program. So let's say we want to find users who, we have the same data sets, right, the click log and the page crawl, and we want to find users who tend to visit good pages. So let's define good as high page rank, and let's say we want users whose visits are on average to high page rank pages. Okay. So conceptually, right, here's sort of a data flow that will give you this answer, right? So a rectangle is some kind of a, it's either the source rectangles are loading data, and the other rectangles are transformations. The arrows represent sets of records. Okay, so roughly, this is sort of isomorphic to that Pig Latin program I showed you earlier, right? You're saying I'm loading the two data sets, I'm canonicalizing the URLs, I'm joining, I'm forming groups according to user. For each group, I'm finding the average page rank, and then I'm filtering. So I just want the users whose average page rank is above some threshold. Right. So hopefully this is fairly straightforward. So the question is, I'm a user. I'm writing up some kind of a program like this that's going to process a large data set. How do I know that I got it right? I mean, so I write something like this, and I want to run it over some large data set, right? Typically, what people do with not just with this kind of programming, but any kind of programming, is that you send it. Well, in the old days, before Eclipse and these dynamic checking things, you sent it to the compiler, and they would come back and say syntax error. So you'd fix all your syntax errors, and then eventually you'd actually run, but they would crash, or maybe it would give you the wrong answer, and you'd iterate many times, and eventually you'd get it to do the right thing, right? So, but the problem is, in this kind of environment where fundamentally you're dealing with many terabytes of data, these sort of test runs, these trial and error runs, can take a very long time, right? And just think of all the carbon you're emitting into the atmosphere by running, on 1,000 machine data center just to see if your program's correct, right? So it would be nice if there was some way that the tool could help you reason about the behavior of your program without having to actually run it, on the data center with the full data, right? So what this is showing you is the exact same data flow program, but now I'm annotating the arrows, which represent these data sets, with sample records, right? And this is showing you, if I had this very tiny input, like these 3 clicks on those 2 web pages, this is what would happen, right? So you're saying, well, I can see canonicalize is going to transform these URL strings like this, right? And then I can see joining is going to tack on this extra field, so I know the page rank, right? I can see grouping. I see grouping forms these nested structures, right? I can see what the average does, and filtering, and right. So I can it makes a much more concrete way of seeing what's happening, right? So if you had, say, forgotten to do the canonicalize, right, then the join result would be empty, right? Because you'd be, or it wouldn't be empty, but it would be smaller. You'd have false negatives, right? So I mean, in general, having concrete examples is always easier than having abstract programs, right? If you teach a class, when you show somebody a program, you show them examples, right? So the interesting question from a research point of view is, can we generate these gray rectangles, these example records, automatically? Okay. So you might think, oh yeah, fine, that's easy, right? I just use sampling. I'll sample the inputs, and I'll just push it through the data flow, and I'll get some sampled outputs and all the intermediate results, right? But the problem is that in general that won't work very well, because Sometimes you have operations like this join here, where if you take a random sample of each of the inputs, chances are the join will not have any matches, right, if the domains are large, right? Or in general, any kind of selective operator, like you have a selective filter, right, sampling you may get empty stuff down here, right? So that's not going to work. Oh, yes, Sergeant.
Understand is that what are you after? I mean, for example, if you just want to know whether a join implementation is correct, I mean, I don't need to know anything in this big terabyte database to figure this out, right?
Yes.
So, but you at the same time talking about random samples. So, is there a specific criteria you have in mind?
Yeah, so unfortunately it's a little difficult to state crisply, but let's assume that the core algorithms are correct. Like I'm trusting that the pig developers implemented join correctly. So what I'm doing is now I'm building my data flows by using these building blocks and composing them. Right, so I'm stacking the group and then the transform and then the filter. And I just want to be able to reason about the behavior of the composed program. I just want to understand things like, I got this canonicalized function out of a library, but I just want to see, like, what does it do? Right, and the easiest way to see that is by looking at examples. Right, or grouping. So grouping, I'm assuming it's implemented correctly, but I don't understand the schema of the output. Like, right, in pig with grouping, we give you a nested output, right? So if you're new to pig or you're new to the grouping operator, you may not be very familiar with that. So if I show you example data, then you can see, oh, I see, it's going to create this nested construct, right? So just in general, it's easier to write a query or a data flow if you can see examples of what the intermediate data looks like. Or you can see, instead of the schema, you actually see data, right? So the idea is just to give you data to illustrate what this thing looks like. One scenario is that you're trying to build this thing and make sure that it does what you intended. Another scenario is that somebody else built it and they left the company. And then you get handed this thing and you want to understand, what does it do? So yeah, there's this program. It does something with data I don't understand, right? So
same question about anything?
No, it's not specific to pig at all. It's any sort of data-centric paradigm, yeah. Yeah, so you could do it in Tioga or whatever. Yeah, right. So I drew these boxes by hand, but how would you generate these automatically? I think that's an interesting question. Sampling, the straightforward sampling doesn't work very well. So the second thing you might try is some kind of reverse reasoning. You say, well, fine, so sampling might give me empty results. So what I'll do is I'll try to put in some constraint at the bottom that says I need some record here that passes this filter, and then I'll sort of work backwards and try to populate things at the top, right? So the problem with that is, the main problem with that is you have these functions, these non-invertible functions. So if you want to do backwards reasoning and you encounter a function that the user gave you as a black box, you don't really know how to go backwards through that function, right? So I think there's this interesting research problem here where the sort of naive approaches don't work very well, right? And you want to generate this data, right? In terms of, so it's a little bit difficult to characterize the objectives, but I think, roughly speaking, you want these three kinds of things. And I have ways to quantify these that, in a paper that we're working on. But roughly speaking, you want the data to be realistic, in the sense that if I showed you some data that was isomorphic to this but had X, Y, Z, it wouldn't be very helpful, right? So you want the data to resemble real data. Now that's different from saying that it has to be real data, right? And that's actually very important because, right, the fact that CNN.com has a PageRank of 0.9 is not important for this particular exercise. So I can make up a PageRank value, right? So you can do some games with synthesizing data, but it should at least resemble real data. Let me go through the metrics and then I'll take your question. The second one is sort of obvious, conciseness. I don't want each of those boxes to have 10,000 records. I want to have a handful of records, right? And completeness roughly says I don't want empty boxes. I want to illustrate all of the results. You have a question?
Yes, I can see that sampling for a large data set raises all the problems you mentioned. But
Okay.
if you work in a company and you look at the internal web, or even better, the internal web inside a division, it gets smaller in a hurry, right? Before you go on the web, go on the Microsoft internal web, or the Yahoo internal web, or even better, on the Microsoft Research internal web, or the Yahoo Cafeteria internal web, right?
Uh-huh.
After a while, it shrinks. And if it's only 100 times smaller than the web, you'll save 99% of the money.
Yes. So, well, just to be clear, I mean, the scenario here is that we have the entire web in a Yahoo data center and we're doing processing over that. But yes, I mean, fundamentally, if you want to use sampling, you want to be able to jointly sample from two things where you're likely to find matches. So if you know enough about the data set, you might be able to do that. But in general, right, treating it as a black box, you have some operations, you have some data that you don't know anything about, you don't know how to do that sampling. In the back?
So it's not really a question, it's more of a connection. So the Haskell people have this tool called QuickCheck that's pretty similar to this. So it's generating automatically, it's generating tests automatically from the declarative specifications of what the inputs.
Yes. Yes. I'd like to see if you can send me a link to that. So there's plenty of work in automated software verification and also hardware. Some of it has a similar flavor. Usually the goal is a little bit different. So here, the idea is that you have some input data set. So all of the software verification stuff that I've encountered, maybe your case is different, but right, is sort of working in the abstract. But here the idea is that you want to actually come up with example data that sort of roughly conforms to some data that you're actually given. Right? And so you work off of that. And you're trying to illustrate all of the intermediate steps. Right? So you're trying to produce sort of realistic and concise examples for each intermediate step. And I don't think there's work in software verification that has that flavor, but I could be wrong. So it'd be great if you could send it to me. Yeah.
I can understand that you want data to sort of test the whole flow of the network, but it seems like you're describing, in the case of that joint example, documentation that should have come along with that primitive operator. In which case, couldn't you just package with it some sample data so when you click on this link, you say...
You could, but in practice, sometimes people forget to do that.
It's much harder problem to try to reverse engineer a black box when there should have just been a short description that said, this is how the steps look like.
Sure. Yeah, so in an ideal world, everything is extremely well documented. And people supply these examples along with all of their code. In reality, I don't think that's really the case. And even if they do, they could be wrong, and so you'd like to test it, right? But yeah, you're right. I mean, so maybe people will start doing that, and we won't need any kind of automated software. Yeah.
Well, I think it's the composition of the whole system that messes you up in data flow systems.
Yeah.
Well, you're also testing the data, right? Because web data is screwy. You want to see when the crazy shit happens.
Yeah, that's right. Yeah, so maybe it works fine on one web crawl that did some cleaning, but there's a new web crawl that doesn't do the cleaning and it breaks what you're trying to do. Yeah. Okay. So anyway, so I'm trying to sort of go breadth first in this talk. So we have some ideas about how to solve this problem. At this point, I'm just trying to introduce the problem and just argue that it's an interesting problem and that sort of simple solutions don't necessarily work very well. Okay, so we have ways of thinking about formalizing this and applying algorithms. But I do want to leave a little bit of room for one last topic, which is sort of at the implementation level, right? We have these Dataflow programs, and we have this language, and as far as executing them. There's various optimizations you can do. Most of them are the sort of boring database optimizations that have been done for decades. I think there's room to do. Let me get into the slides and talk about optimizing ensembles of programs. So before I get there, just so people are on the same page, the way that the system works is that a pig-Latin program comes in. Okay, we have a parser, just like standard stuff. We compile a pig-Latin program into what we call an execution plan, which, if you're not a database person, right, it's some kind of a tree of algorithms that are processing data, starting from raw data that's stored on disk and producing a sort of series of derived data sets, right? And then we have a second compiler that takes something like this and compiles it into one or more MapReduce jobs. Okay, and roughly speaking, the objective of this one is just to minimize the number of MapReduce jobs, because each MapReduce job is a pass over the data. Okay, roughly speaking. And then we use Hadoop as our MapReduce implementation to actually run this on the cluster. Okay, so what I'm going to talk about for the rest of the talk is something that we're working on to put inside our compiler, which we call our cross-job optimizer. Okay, so instead of taking one job at a time and compiling and optimizing it, we're going to look at ensembles of multiple related jobs. Okay. So let me start by motivating why this is important. Right? So first of all, if you look at what people are doing with MapReduce and Pig at Yahoo, and I suspect it's very similar at Microsoft and at Google, we have a lot of tables in our system, data sets, but there's only a few of them where most of the action happens, right? There's like the web crawl and the click logs and the search logs of what people are searching for, like Britney Spears, as you all know, right? And so you have a lot of action on these handful of very large data sets. And if you look at the way these MapReduce systems are processing these, right, they have a queue, like a FIFO queue or maybe a smarter queue of pending requests. And at any given time, the system is handling one or two of those requests. The request is sort of this thing where you scan this very large data set and you do some processing. Sometimes the processing you're doing is fairly complex and expensive, like face detection. A lot of times it's very cheap processing, like you're counting something, like how many times did Britney Spears occur on the web, right? So in those cases, the work is mostly I/O bound. Like most of the resources are going into just doing the scans, right? And so what you have is a queue of jobs, all half of them waiting to scan the same thing that the current job is scanning, right? And so you're doing the scan of these files over and over again, each time to do one job's sort of relatively simple processing, right? So there's an obvious opportunity there to amortize the scan across many jobs, right? And the same is true if you look not just at the data that's being accessed, but also the way the data is being transformed. You see the same transformations over and over again, right? So, and in fact, so things like, okay, I want to process the web, but I want to filter out the spam, right? Or I want to do group-wise or host-wise processing of web pages instead of one URL at a time, right? So when I first got to Yahoo, I wanted to run a bunch of processing on the web, and I asked somebody that I knew in the development group, hey, can you send me some code or something that will suck the web out and let me process it? And he gave me code that did a bunch of stuff like this. And he said, oh, paste your part at the end, right? So, you want to eliminate spam and group by host and then do some processing, right? So you have people independently submitting these jobs that have a common prefix. And obviously there's redundant work going on, right? So we want to try to minimize that work, right? So in databases, it's called multi-query optimization. You can roughly think of 3 kinds of techniques that you can use to try to minimize redundant work. One of them is you can take jobs that are similar, meaning perhaps they access the same data set, and you can run them jointly instead of running them separately. So you only do the scan of the data set once, and then you do the processing after that. Right? So you save one scan of the data set. A second kind of thing you can do is you can say, well, look, I've got these 2 jobs that have some common prefix, like both of them filter the spam and group by host. And so to avoid doing that same work multiple times, I'm going to cache some intermediate result. Like I'm going to cache A prime, which is derived by applying operator 1 to A. Right, so in databases, this is called a materialized view. Okay. And a third kind of thing you can do, remember, underneath all of this, we have a parallel system running on many machines, right? So the data lives on many machines, processing is occurring on many machines. So sometimes you have situations like this where you've got these data blocks, A, B, C, D, spread across these worker nodes. Right? And when you have some kind of processing you have to do, that has to get scheduled somewhere, right? So for example, maybe worker 1 is really busy because people are scanning D. And you have some request that requires processing A and B together, right? So maybe that gets scheduled over here, right? Because this machine is idle, right? So in order to make this happen, right, A has to get copied over here, at least temporarily, so that you can perform this operation, right? So here you have an opportunity to, if you believe that there's some stationarity in the workload where combining A and B is going to be a common thing, like maybe A and B are related data sets that get joined often, then it may make sense to have A and B co-located together, going forward in the future, right? So you can think about the placement of the data with respect to the workload that you're seeing. Okay. So let's see. So I guess I want to wrap up because it's been almost an hour, but from a database perspective, most of these techniques are not new, okay? And I'm not really so much interested in the mechanisms here. Okay, what I'm interested in is the process of deciding when to apply these techniques. Okay, so you have these. Think about having a sort of a MapReduce Pig kind of system that has these weapons, right? You can use these things to avoid doing redundant work, avoid redundant scans, or avoid redundant transformations, right? Or avoid redundant data movements in the cluster. So the question is, when would you apply these things? And I think at a high level, the kinds of ways that database systems tend to think about deciding when to apply these things are not always going to succeed in this kind of environment because of the nature of the jobs. They tend to be much more opaque in general than database kinds of jobs because they have so many user-defined processing elements. And also because of the nature of the environment. You have this much more chaotic environment with thousands of machines, some of which are up, some of which are down. You have, the network saturation is sort of moving around, the bottlenecks are shifting. So so what I'm interested in is, rather than looking at approaches based on sort of modeling and planning to decide when to apply these techniques, looking at approaches that are more adaptive that for applying these techniques. So I can talk in more detail about that, but just, to avoid having the talk take a long time, maybe I'll just skip to the end. So I've gone through a lot of things. Just let me go back and summarize the main points here. So I started by talking about a data parallel language, which we call Pig Latin. And the idea is that users are specifying these sort of general sequences of transformations on data. Okay? And they can use a combination of standard relational style primitives as well as interleaving that with custom code. Okay? I talked about a development environment where users can develop their programs. And the interesting thing there from the research perspective was, can you automatically generate example data to illustrate how the data flow is going to transform the data through the intermediate results? Okay. And then at the end, I talked a little bit about runtime optimizations. So in particular, given that you have a set of related programs, how can you amortize the work that's being done redundantly in those programs? Okay. And obviously, I'm not doing this work by myself. I have a bunch of people working on this. So these are my colleagues, and glad to take any last questions that people have.
The optimization for caching the moves. So what I know from HDFS, doesn't the distributed file system take care of that?
In the short term, certainly. So it takes care of, so the distributed file system, right, makes the location of these blocks transparent to the thing that's executing. So the fact that you're trying to join A and B here, but A doesn't have a local copy, right, it'll automatically take care of fetching A from somewhere else, right?
But even like in the map Hadoop is supposed to take care that the operation takes place on the temporal locality. I mean, the spatial locality is taken care of.
Yes, but see, Hadoop is very much fixated on operations that have one input. But in practice, people do joins all the time, right? And so here, tell me how to do the join such that A and B are both local, right? You can't. But if you anticipate that joining A and B is going to be a common thing over, repeated over time, perhaps you should think about reorganizing the data such that A and B are local, right? And then even more sophisticated, you can say, well, look, I have 3 copies of A and 3 copies of B because that's how I'm doing fault tolerance. So maybe some of the pairs are local and some of them are not, right? And so there's all kinds of interesting games you can get into, and you can think about both sort of static ways of planning that and also adaptive ways of doing it, right?
I guess my doubt is, where do you think this optimization should take place? Should it take place at, should people take care of it, or should the Hadoop people take care of it?
You can make the argument for either way. I don't think the optimization is specific to Pig, but Pig makes it easier to express joins, so you're more likely to encounter them. Yeah. Yeah.
So it seems like you make MapReduce and Dataflow synonymous, at least in this work. I wonder if you would get any leverage out of using more general forms of Dataflow that of which there are many different types. So if you wanted, for example, to have a control loop, you can use a version of Dataflow that's no longer just MapReduce, where you can even analyze that system and say with a deadlock, or introduce FIFOs between the links and know.
FIFOs between the links?
Yeah, so in between passing data, I assume these are finite links between the nodes, right? You have to pass some data to the other node that's hungry. And so if you have too much data, you overflow this link, and then the system does something that is completely different from MapReduce at that point. So more general all I'm saying is that there are more general data flow languages out there that, that go beyond that model and can provide additional.
Sure. So what if you remember from earlier? So I was saying that so Pig is fundamentally a directed acyclic data flow. So it does not allow cycles. We have so far encountered exactly one case where people wanted cycles, which was for a PageRank computation, an iterative computation. And we have the embedding property, so you can embed in a programming language that has control loops. So, of course, then doing optimization across the levels is going to be hard. So, so far it doesn't seem like, in practice for us at least, there's a lot of motivation for looking at doing complicated sort of optimization of control structures in Pig, just because we haven't encountered a lot of people who need those kinds of control structures. Perhaps as users get more sophisticated, they'll start wanting more and more of that. I don't know at this point. But one thing that's actually important to point out is the way that Pig does the execution is what we call lazy execution. So the way you specify a Pig program is you give it a sequence of steps, right, which can refer to variables defined in previous steps. And there's a special command called store, which says take a variable and materialize it on disk. Pig will not actually do anything other than parse your program until you say store. Okay? And the reason we can get away with that is because the data is basically static. We don't deal with updates, right? But the advantage of doing that is we can do optimization of large fragments of programs. And where this ties together your question, in the PageRank example where you have a loop in Java that's spitting out Pig commands, right? You'll see actually, assuming you know in advance how many iterations you want to do, or maybe you want to do 10 iterations and then check for convergence, we can actually optimize across all 10 iterations. So effectively, we're doing loop unrolling, right? So we can get some of the advantages for free in some sense. I don't know if that pertains to your question or not, but yeah.
On the data movement you described here with the join and also materialized views,
Uh-huh.
are you thinking that these would happen when the data is loaded into the system, or that it would happen lazily?
Well, you can think of both. I think both are interesting. And certainly in the database world, you've seen plenty of work on these mechanisms for doing, so for selecting materialized views. In fact, Surajit has done a lot of that work. And data placement sort of in the sort of planning stage, right? You're populating the database, you have some anticipated workload, or maybe periodically you look at the workload and you try to optimize based on that. And I think that makes a lot of sense. I'm interested in looking at, well, can you, in addition to that, can you do things that are more adaptive, right? As conditions are changing, you're seeing different workload characteristics, or maybe you knew what the workload was going to be, but you didn't have a good model for how it was going to behave until you actually ran it, right? So maybe sort of reactively, right, try to adjust your plans in terms of what data you're caching or where the data is being located. So, and I think that's where there's more room for interesting research that hasn't been done already.
Thank you, speaker.
Okay.